Today we're going to finish the material we started last time, which was solids of revolution, talking about the shell method, and we have one more example. We're going to use the shell method to set up and evaluate an integral, and the solid we're going to generate is bounded by the curves y equals x squared and y equals 4x minus x squared, and we're going to revolve this around the line x equals 4. So the first thing I want to do is I want to sort of draw this region and identify what we're looking at. So for y equals x squared, we've got a graph that looks something like this. And then for the other one, the 4x minus x squared, we're looking at a graph that looks something like this. And so what you notice is that there are two locations where these two graphs cross one another, and in order to find out exactly where that happens and not just speculate based on a picture, we need to find out where those two equations are actually equal. So we're going to take the x squared and the 4x minus x squared and set those equal to one another. And we're doing this, we're going to move everything to the left-hand side, so that's going to give me 2x squared on the left minus 4x, and that equals 0. And of course we have to factor this, so we'll factor out a 2x, which leaves me with x minus 2 equals 0. So x equals 0 and x equals to 2. So this first location right here is at 0. And you'll notice very quickly if I plug x equals 0 into either of my equations, but in particular the first one's awfully nice to do, so I very quickly find out that that's actually at y equals 0 as well. And we can do the same sort of thing right here. At this point I'm going to plug in x equal to 2, and I very quickly can find out that y equals to 4. So that is my region in between here that I'm going to be finding my area of. Now, this is an awfully tiny graph, so I need a little bit more to go on to be able to talk about it. So I'm going to draw just the corner of them intersecting right now so that we can identify things a little bit more clearly. So I've got a graph that looks something like this and a piece that looks something like this. Now, unfortunately, the way I've drawn my graph, I can't see where my line was going to be, and I'm supposed to have this line at x equals to 4. So let me move this to the next slide, and that should help us some. Alright, so I'm supposed to then come out here at x equals to 4 and draw a vertical line, and we'll draw that in a different color just so that we're remembering that it means something different. So over here, and we'll say about right here, we've got the line x equal to 4. And we're going to revolve around this line. So in cylindrical shells, of course, we need to make a rectangle that is parallel rather, to the axis of rotation. So we've got a rectangle that looks something like this. It sort of looks like I've got a leaf going on here. And we're looking at the radius and the height. So the height of the rectangle itself, h of x, and this is in terms of x because the distance right here is delta x. So this h of x equation over here is actually the top equation, which was 4x minus x squared, and then to subtract off the bottom equation, which was just x squared. So my height is actually 4x minus 2x squared. Now the radius is actually going to be this length right here. And my radius is actually found by taking a look at how far we are away from the axis of rotation. So obviously no matter where we are, we're not more than 4 away from the axis of rotation, because this distance right here is 4. So that piece is right there, 4. And this piece right here is x. So my radius in blue would actually be 4 minus x. So that is r of x. So I'm going to create an integral. I want the integral, my volume is what I'm looking to find, and I want my integral of, I want 2 pi times my integral. This is in terms of x, so my x is actually starting at 0, and I don't have it marked out here now on this graph, but I will. It's going out to 2, so 0 to 2, of my radius, r of x, which was 4 minus x, times my height, which was 4x minus 2x squared, dx. Alright, so we're going to have to FOIL that out before we can integrate, so that's where we are now. We're going to integrate this from 0 to 2, and if I FOIL this out, I'm going to end up getting 16x minus 4x squared and minus 8x squared, so that's minus 12x squared from my inner and outer terms, and then plus 2x cubed. And we integrate, so this will end up being 8x squared minus 4x cubed and plus 1/2 x to the 4th, and we're supposed to evaluate this from 2 down to 0. Alright, so clearly the 0 is really nice here because when I plug in the 0 I don't end up getting anything. But I do end up getting portions of this when I plug in 2. So this is 8 times 2 squared minus 4 times 2 cubed plus 1/2 times 2 to the 4th, and then I've got actually here minus 0. Alright, I think I got enough parentheses there anyway. Alright, so this is 2 pi. I have 8 times 4, which is 32, minus 4 times 8, which is 32, plus 1/2 times 2 to the 4th, which is the same as 2 to the 3rd, or 8. That all ends up being 2 pi times 8, which gives me 16 pi. And of course, as we've talked about in class, we can double check that against what the calculator would give us if we put in our original setup equation and see what we would end up with for there. And we will also find that that is 16 pi.